Module 1, Fundamentals of Precision Agriculture. Definition and Scope. Definition. Precision agriculture, PA, also known as precision farming, is a farm management approach that leverages digital technologies to monitor and optimize agricultural production processes on a site-specific basis. PA is an advanced innovation and optimized field-level management strategy used in agriculture that aims to improve the productivity of resources on agricultural fields while minimizing disruption to the agro-ecosystem. PA typically focuses on optimizing the use of farm inputs like fertilizers, herbicides, seeds, and fuel, utilized in activities such as tillage, planting, spraying, etc., by implementing the right management practices at the right place and at the right time, leading to better environmental quality. PA can also be defined as the use of information technology to enhance the management of crop and livestock production. It is recognized as a vital tool for advancing global food security, with the potential to boost productivity, optimize farm input use, e.g., pesticides, fertilizers, water, feed, and labor, stabilize production, and minimize the environmental impact of agricultural practices. PA relies on extensive data and information to enhance resource efficiency, improve crop yields, and ensure better crop quality. By integrating data from various sources, PA aims to boost crop productivity and cost-effectiveness through strategies such as efficient fertilizer use, irrigation management, and targeted pesticide application. Although definitions of PA vary, the term typically refers to tools and methods applied locally at subfield scales, i.e., less than 5 meters. Scope. PA can generally be categorized into 3 stages based on data collection and site-specific activities conducted before, during, and after the crop growth period. These stages are the preparatory or pre-planting stage, the crop growth stage, and the harvesting stage. First, preparatory stage. This planning phase involves data collection prior to planting, focusing on factors such as soil nutrient status, groundwater availability, previous crops and their residual effects, and the presence of pests, diseases, and problematic weeds that could impact the yield of the crop to be planted. Second, crop growth stage. During this phase, data collected in the preparatory stage is utilized through Geographic Information Systems, GIS, to design and implement management practices for irrigation, soil fertility, and protection against biotic and abiotic stresses. Third, harvesting stage. This final phase has 2 key objectives: assessing the final yield resulting from the season's precision practices, and using this yield data to develop strategies for the next cropping season. PA is an approach in which the actual adoption varies significantly based on farm characteristics, including the types of crops or livestock, farm size, management style, access to technical support, and the operator's attributes, such as age and education, among other variables. Consequently, PA adoption differs widely among farms and has been slower and less uniform compared to other agricultural innovations. Modern PA systems are rarely implemented on small, low-mechanization farms, which constitute a significant portion of global agricultural production, particularly in regions that are most food insecure. Like other agricultural technologies, PA primarily benefits its adopters and society at large, but farmers who cannot or do not adopt it are often left at a disadvantage. Unfortunately, this includes many farmers worldwide. Unlike earlier agricultural innovations focused solely on production, PA's information-driven foundation enables it to inform and adapt processes across the entire food supply and demand chain, providing a broader capacity to address food security challenges. PA can be applied throughout all phases of the crop production cycle and used to accurately document field operations. The concept leverages recent advancements in sensors, greenhouse technology, and protected agricultural structures. PA identifies and maps spatial variability within a field, enabling the adoption of site-specific management practices using tools such as global positioning systems, GPS, GIS, and remote sensing, including the use of variable rate technology, VRT. This approach thus focuses on optimizing economic and environmental benefits by reducing the use of farm inputs. Instead of applying inputs uniformly across an entire field based on an assumed average condition, PA tailors management actions to the specific needs of different areas within the field. The combination of GPS and GIS in precision agriculture enables precise mapping, real-time analysis, and improved decision-making. The scope of PA also varies across countries due to factors such as socioeconomic conditions, availability of skilled personnel, and landholding sizes. Despite the potential of precision agriculture technologies, PATS, Adoption rates vary significantly across regions and between different technologies. Furthermore, PA relies on extensive information about crop conditions or health during the growing season, collected at high spatial resolution. Regardless of the data source, the primary goal of PA is to assist farmers in effectively managing their operations. This support can take various forms, but it generally results in reduced resource usage as illustrated in the figure, which depicts the precision agriculture farming cycle. The precision agriculture management approach currently relies almost entirely on the private sector, which offers services, devices, and products to the farmers. Public sector involvement is generally very limited, notwithstanding the growing policy interest in the role of innovations for increasing productivity and sustainability. Available data on adoption rates are fragmented and often dated because countries do not regularly collect data on the use of precision agriculture, with manufacturers and precision agriculture dealers rarely revealing their sales data. Evidence on the use of PA relies mainly on information from sporadic and geographically dispersed surveys. Hence, an accurate measurement of the rate of adoption and the various technological practices is thus problematic. North America currently represents the largest market for PATs, with the United States leading in adoption. In Europe, Germany, France, and Denmark are at the forefront of implementation. Similarly, within the United Kingdom, Scotland and Ireland have the highest adoption rates. In South America, Argentina and Brazil exhibit significant adoption of these technologies. However, in Africa, adoption of PATs is fairly low, with South Africa taking the lead. Historical development. The origin of PA can be traced back to the mid-1980s. Dr. Pierre Robert, often regarded as the father of modern precision farming, first conceptualized PA during his college years. He spent many years researching and developing its principles, emphasizing the use of technology to analyze soil variability, germination, drainage, and other factors critical to crop success. Dr. Robert proposed shifting from a blanket application of resources to a targeted approach, focusing on underperforming crops to optimize their growth while preserving healthy crops. This strategy aimed to allocate resources more effectively, improving overall crop management. However, like many groundbreaking ideas, the concept faced challenges. While promising on paper, precision farming at the time was limited by technological constraints, necessitating advancements in equipment to fully realize its potential. The term precision agriculture was first introduced as the title of a workshop held by the State College of Montana in 1990. The advancement of modern PA was significantly influenced by progress in information technologies. A major milestone in its development came in 1983 when U.S. President Ronald Reagan announced that GPS would be made available for civilian use. By 1991, the first GPS receivers were integrated into tractors, and in the mid-1990s, the U.S. Department of Defense removed selective availability for differential GPS, DGPS, improving positioning accuracy from 5 to 10 meters. Further advancements in accuracy followed in the 2000s. The 20th century saw the emergence of Agriculture 3.0, ushering in a new era of more efficient and intelligent machinery operations. PA during this period incorporated technologies such as satellite navigation, sensor and control systems, and data management tools. The integration of information and communication technologies, ICT, facilitated automation and robotics, enabling efficient task repetition and production process monitoring. Agriculture 3.0 also introduced a paradigm shift, moving the focus beyond production and sustainability to emphasize soil health and resilience. This evolution reflects the transformative impact of technology on modern agricultural practices. Nevertheless, PA is recognized as one of the top 10 agricultural revolutions, despite its commercial adoption beginning only in the 1990s. Importance in modern agriculture. Modern agriculture faces the urgent challenge of meeting the growing global demand for food, while also addressing resource scarcity and promoting sustainable farming practices, especially in a time when the costs of pesticides, herbicides, and seeds are rising. PA offers a solution by enhancing crop productivity and farm profitability through more efficient management of farm inputs. This leads to improved environmental quality. Farmers also perceive additional benefits, including more precise hybrid selection, rental agreements that align better with actual soil productivity, optimized fertilizer applications matched to crop yield potential, lower chemical expenses, reduced fuel costs, and less soil compaction. Societal benefits include the creation of high-tech jobs in areas like computer hardware, software, machinery guidance, soil and crop sensors, information management, and decision support systems. PA also helps mitigate environmental pollution caused by the overapplication of nitrogen and phosphorus fertilizers. By using high-tech equipment, PA reduces agricultural inputs through site-specific applications that target the spatial and temporal needs of fields, which can result in lower greenhouse gas emissions. PA also positively impacts farm productivity and economics, offering equal or higher yields at a lower production cost compared to conventional farming practices. Thus, PA plays a crucial role by leveraging intensive data collection and processing in both time and space to make farm inputs more efficient, ultimately leading to better crop production and environmental outcomes. We have come to the end of the introductory part of this module. Stay tuned for the other parts.